Today I'm going to give you an easy, but crazy, explanation of the fundamental theorem of calculus. It doesn't need to be crazy, but I like to add crazy stuff in anyway. Suppose you live in a fairy tale world where instead of growing taller every year until you reach adulthood, there are some years you grow and some years you shrink, and there's no consistent height you reach at maturity. Let's also suppose that in this world, you and all the other creatures in it are half ant and half pig. Okay, I think that's enough crazy for now. Now we can start with the math. Now let's say in this strange land you start 3 feet tall at birth. The next year you grow 2 feet. Then you grow 5 feet. Then you shrink 2 feet. Then you grow 4 feet. Then you shrink 3 feet. Then you grow 8 feet. Finally, you shrink 1 foot. How tall are you after all those years? Simple addition and subtraction. Why not do it on a calculator to keep things easy? You get 3 plus 2 plus 5 minus 2 plus 4 minus 3 plus 8 minus 1 equals 16. See, everything is crazy but easy so far. I know I'm using a lot of numbers here, but I want to show that this works no matter how many numbers you use. Now here's the next question, and it's a big one. How much did you grow from birth until the last year we've tracked? Still simple. Just take the height at the end and subtract the height at the beginning. That's usually how you find out how much something changed. 16 minus 3 equals 13. You grew 13 feet between birth until now. And now we arrive at the key point of the video, and it requires the most thought. There's another way to get that same 13 feet answer. Add up all of the changes that were made every year, and they equal the total change from 3 to 16. Well, you started at 3 feet, and that's just where you started. It's not a change, so it doesn't factor into the calculation. The first change that happens is when you grow 2 feet. Then you grow 5 feet, and so on. So adding up all the changes looks very similar to the original problem of us figuring out how tall we eventually got. Now all we're doing is taking off the 3 at the beginning. That gives us 2 plus 5 minus 2 plus 4 minus 3 plus 8 minus 1. Sure enough, it equals 13. So we used 2 different methods, and both of those methods gave us the total change in height of 13 feet from our starting point to our ending point. Well, what do you know? This calculation right here is just an example, a parable if you will, that shows that the total change that happens to something can be measured in 2 different ways. We can either take the value at the end of the changes, 16, and subtract the value at the beginning, 3, or we can just sum up all the little changes that happened along the way. 2 plus 5 minus 2 plus 4 minus 3 plus 8 minus 1. Either method will give us the number 13, which was the total change. So, since both give the total change, we can say both methods are equivalent to each other. In other words, the sum of all the little changes between 2 points is equal to the difference between the end value and the beginning value. This is simply a law of nature, and it always works. And that is what the fundamental theorem of calculus actually says. The sum of all the little changes between 2 points is equal to the difference between the end value and the beginning value. Let's take a look at the actual formula now to see if that's really what's being said. See that weird looking S thing there? That means sum. that f prime of x is a function that means all the changes between points. It's known as the derivative. The little a below the s is the starting point, and the little b above it is the ending point. We are looking at all of the changes between those 2 points. And on the other side of the equation, we see f of b minus f of a. F of something is the value of it. So that part of the statement is read, the difference between the value of b, our ending point, and the value of a, our starting point. So the fundamental theorem of calculus really does say the sum of all the little changes between 2 points is equal to the difference between the end value and the beginning value. And amazingly, we didn't even use a bit of calculus to figure that out. So the fundamental theorem of calculus has been explained in the easiest way I can think of. I hope you've enjoyed it. However, I'd like to go just a little bit deeper for anyone who is still interested. It's not quite as easy as the stuff I've gone over, but certain viewers may get something out of it. I've just shown that the idea behind the statement of the fundamental theorem of calculus is true in the discrete world, where numbers can actually be counted in order. This consists of whole numbers and integers and stuff like that. But there's another world out there called the continuous world, and it deals with decimals and fractions and stuff. It's really tough to write these in any kind of order from smallest to biggest. I mean, what's the number that comes after 2.53? Is it 2.54? 2.531? 2.5300000001? The real beauty of the fundamental theorem of calculus is it's true in the continuous world as well, not just the discrete world, and that's where the actual calculus comes in. Calculus involves something exceedingly brilliant called limits to overcome the issue in the continuous world of not being able to put numbers in order of size, since you can just keep finding numbers in between them. The small changes represented by f prime of x in the formula are taken down to an infinitely small limit, and that's as far as I'm going to go in this video. One last thing for the math purists out there who are probably mad at me for leaving the dx off after the f prime of x. Go yell at Albert Einstein for leaving off the sigma notation symbols whenever he used his Einstein summation convention. I'm trying to keep stuff simple.